Okay, so let's start. So today we want to learn just these three things. First, we want to look at linear systems, and with linear systems, we're not going to go much into the details of it. We are now aware of what we mean actually when we talk of linear systems, and we are also aware of how we can go about solving all those types of systems. So today, the first thing that I just want to talk about when it comes to linear system is the nature of their solutions. So we want to talk about the nature of the solutions of linear systems. So that's the first item of study. So what is it that we have to understand when it comes to linear systems? You see, so one thing that we have to know is that a given linear system can have 0, 1, or infinitely many solutions. You see, so when it comes to this group of objects that we refer to as linear systems in mathematics, there is one thing that you just have to be aware of, which is very much important when it comes to their study, which is the nature of their solution. So one thing that you should know is that these objects that we refer to as linear system, their solutions, they always obey this property. It's either we do not have any solutions at all for a given linear system, or we have one solution, or we have infinitely many, which means for anything that is called a linear system, there are always these three possibilities that are associated with it. Either you won't have any solution, or you'll have one solution, or you'll have infinitely many solutions. So it is something quite intriguing, because one might expect that maybe there is a possibility of having 2 solutions, 3 solutions, or 4 maybe, but this, what we are stating here, it actually tells us that there are only 3 options for the solution. It's either you don't have it all, or you have one, or you have infinitely many. So that's the nature of the solutions of anything that is called a linear system. It is always going to be associated with either one of these, you see. So the question is, how can we prove this result now? How can we prove that actually this result is true? Because it's one familiar problem in mathematics, whereby they can give you this statement, which we know and we are very clear that it's true, but how can we prove that actually this is true? You see, how can we prove that this is the case all the time? So first, before we go on to rigorous writing, I will first look at this problem in 3-dimensional space, you see. So when it comes to 3-dimensional space, what do you understand about linear system when it comes to that context, especially now inclining to the geometrical view of things? What do you understand about linear systems in the geometrically when we talk of 3-dimensional space now?
There's an X, a Y, and a Z coordinate.
Yes, but what exactly is are linear systems when we start bringing in the geometrical language, and we're talking about 3-dimensional space? What are those objects actually when we are to represent them geometrically? What are they?
Are they matrices?
They are not matrices, because matrix is something which is not geometrical. You see, it's still an algebraic object. You see, but now we want to bring things into a new world, geometrical world, where things you have a visual appearance. You see, or they have a physical meaning, which is different from the one that we know in the mathematical world, where everything is represented by either an algebraic symbol or a number. But now when we are to shift from this space, which we always work with, of numbers and letters, and we shift onto the geometrical space, where things, they take different forms, You see, where objects appear visually in different shapes or distinct objects, like linear systems in 3 dimensions, in what form do they appear in when we bring them in the geometrical space? That's one thing that you have to understand. You see, so 3-dimensional system, when you bring them in a geometrical space, they are represented as planes, you see. So what we refer to as a plane is just a linear system. Remember, this thing appears like this when we talk about geometrical picture. When we move on to the metrical picture, that's where it takes the form ax plus by plus cz is equals to d, you see. So that's how it appears when we are in this world of algebra. But when we shift onto a geometrical world, this thing is recognized as something like this, just a simple plane. Do you get that?
Yes, I do now.
Yes. So, so you will see that if now you have this understanding, you can actually verify this thing that is actually true. You see that? Suppose I give you 3 planes and I want you to orient these planes in space. Do you see that if you look at these planes, suppose I say arrange them such that they have a common point between them, or they have none at all, then you will see that actually this result can be verified. You see that? Because if I give you 3 planes, there are 3 possible arrangements that you can do with all of them. It's either you arrange all of them in parallel. So if all of them, they're in parallel, there is no common point of intersection between these 3. So that's the case which we refer to as having no solutions at all. Do you see that? At times, I can represent these 3 planes to intersect one common point like that. So all my planes, if they pass through one common line, then I say I have 1 solution. And the other thing that I can do is I can lay all of them on top of each other, one on top of this, one on top of that. So if I ask you now, how many points of intersection are there? There are infinitely many, because these planes, they are not fixed, you see, or they do not have a fixed ending. They are just penetrating the whole of space infinitely in all directions. So if I ask you now, how many points do they have in common where they intersect, you will see that there are infinitely many, you see. But are these the only possible arrangements? These are not the only possible arrangement. I can intersect the 2 planes while the other one goes it's in one side. You see that? But now when we talk about trying to arrange them such that they have a point in common or a line in common, then there are only 3 ways available. It's either they do not have a point at all, or they satisfy, or they all pass through one common point, or they share infinitely many points. Those are the only ways they can be arranged in such a way that 3 of them, they have something in common. You see. So this is the idea that can make you understand that this result is actually true. But how can we prove it? How can we prove it? So to prove this result, this is how we proceed. So to prove a result like this one, we are not going to bother ourselves with looking at the 2 cases, which is proving that there can be no solutions at all, or they can be 1 solution at all. But we are going to prove actually that if we try to consider a system with 2 solutions, we'll see that the 2 solutions, they always imply that infinitely many possibilities are there. You see that? Because the nice thing about this result is that it says that 0, 1, but not 2 at all. After 1, infinitely many solutions arise. So which means one way of trying to prove this result is to show that any given system can never have at max 2 solutions. You see, so if you happen to prove that this linear system that's given to you can never have 2 solutions at max, then you have actually proved the result that you are trying to look for. So this is one thing that you must understand, because it's a common problem. And the reason why most people, they find it hard to answer this problem is because you have to be aware of the problem that you have to answer in order to answer the whole thing. So if you try to look at all the cases of trying to prove that there is no solution at all, it's very hard to prove that. And then to prove that there is one solution, it's very hard. But those are things that you can explain. A proof sometimes can have a few lines of you explaining that, okay, this can be the case. You see that? This can be the case. So remember, one thing that we know about system is that systems can be written in the form AX plus is equals to B. So one thing about the systems that we're looking at this section is that all of them, they can be written in the form AX is equals to B, where X and B are vectors like that. You see. So now, how can we answer the first two cases to prove that an equation like this cannot have any solution at all? So you can explain. And remember, if you take a matrix and multiply a vector, what is the result?
Wouldn't it be a vector?
It will be a vector. But are we guaranteed that all vectors that come from any matrix A with some vector will always give us a vector which is equal to the vector on the other side?
I don't think so. I think there's some examples that give colors.
Yes. So it's not guaranteed. You see that?
Yeah.
So which means we have seen that it may happen in some cases that what we have on the left cannot equal what we have on the right. So no solution at all. Do you see that?
Yes.
So we see that the first case, we're done with that. Now, suppose this matrix A involved is actually the identity matrix. Suppose A is equal to I. What does it mean? Do you see that X will just be called B? So we have one unique solution in this case. Do you agree on that?
Yes, I do.
So we see that when the matrix involved is equal to the identity matrix, then we have one solution. So the two cases, they have been catered for. Now let's look at the final case. How can we prove the final case now? So what I'm going to do now to prove this final case, we are going to approach this way. So now we'll say again, suppose X1 and X2 are solutions to our system, and that X1 is not equal to X2. So now what I'm going to do now is I'm going to now look at the most important problem that we want to solve. The problem of trying to show that it is impossible to have only two solutions. Two solutions will imply infinitely many solutions are possible. You see. So now what we have done here, we've considered two solutions. We've assumed that we have two solutions to this linear system that we're solving. So what we're going to do now is we're going to use these two and show that with these two, actually, there are infinitely many possibilities possible. You see. So now let's come back. So what does it mean? So now we have supposed that these two solutions that are here, they are a solution to this thing. So what does it mean? So it implies that AX1 will give us B, and also it means that AX2 will give us the vector B. That's what it means if these two are solutions. It means when you take matrix A and multiply this, you'll get B, and you take this and get that multiply B, but these are not equal. So we'll keep it like that. So now what we're going to do is we're going to build a solution using these two that we know that a solution. So now let's consider this solution. So I'll call it big vector X, which is defined as follows. It is the sum of X1 plus T bracket X2 minus x1. So what I'm going to do now is I have created a new vector using the two vectors that I know they're actually solutions. And this t that you see there can take any value which is a real number, like that. So what I'm going to then prove is that we are going to prove then now that this thing that we've created here is actually another solution to that, to this equation. So how can we show that this is actually another solution? So to show now, I'm going to multiply by a both sides. So if I multiply by a both sides, I'll get a times big X is equal to a x1 plus t bracket a x2 minus x1, like that. So what does that give us? Remember, this thing is a solution. So the product of a times x1, we know that it will give us a b. So we get b plus t times a gets inside by distributive property. So we get ax2 minus ax1, like that. Yes, we know that the two vectors x2 and a, they are quite different. But what do we know? We know that ax2 will give us b, and we know that this will give us b. So this will vanish, and the only thing that remains with is just b. So what happens now? So finally, what have we achieved? So finally, we see that a times big X gives us b again. So what conclusion can you make from that? So do you see that from here, we can conclude that big X is another solution to this linear system?
Yes, yes.
Easy. So now let's go back and analyze X. What is actually X? Do you see that X is not just one fixed vector? Is that clear? Because look here.
Yes.
T is just a parameter which I can change anytime. So this thing, which is dependent on some parameter t, we have proved that it's a solution. So which means this equation that we have here cannot just assume two solutions. With two solutions, it implies you have actually managed to get many other solutions to that, which can be found by creating or arranging them in this format, like this. So with this that we've done here, we've actually proved that result, that for any given linear system, either you don't have a solution, or you have one, or you have infinitely many solutions, you see. So therefore, the result falls. So this is something that you have to know how to do in exams to show that this result is true by using matrix notation. So are we clear with this result?
Yes, yes.
Okay, cool. So the next thing that we want to talk about is the importance of the echelon form in problem solvents. You see, so importance of the echelon form, like that. So you will see that in the goal of learning how to solve linear system, one of the concepts that we're taught is the reduction or the rewriting of a given matrix in a form which we refer to as the echelon form, you see. So today we want to understand why is it actually important for us to always take whatever matrix is given and express it in this echelon form, you see. Or sometimes which we can further reduce to what we call the reduced echelon form. But what is the importance of this format anyway? So the first thing that I know that you are aware of is that it is easier to solve systems that are in echelon form than the ones that are not in that form. You see, because when a system is in echelon form, we can use what we call a backward substitution to solve the system. You see, but is that all that the echelon form can do for us? That's the question, you see. So the echelon form cannot only do that, you see. So what we refer to as the echelon form of a matrix is a form which can actually tell us about the existence of solutions, you see. So if you are given a system and you are interested in knowing whether there is no solution, whether there is one solution, or whether there are infinitely many solutions, the echelon form, if you are to study the echelon form of any given system, it can tell you everything that you need to know. But the question is how? How can you learn about the solutions of a given system from its echelon form? So I think that one you might have an idea. How do we tell about the nature of a solution from the echelon form, if I may ask?
It would be in its simplest form. The zeros would generally be at the bottom. There would be pivots. So the leftmost upper, it'll start and it'll go down in a ladder shape, not ladder, but like a step type of thing, with free variables generally on the sides.
Yeah. So, so suppose we have a linear system with n variables. So suppose we have a linear system with n variables like that. Then there are three cases that can arise when you are to consider that system and you express it in its echelon form. There are always three important cases that can arise most of the time. And what are those three cases? So the first case that can arise when you are working with a linear system and you are trying to express them in their echelon form is that you may get a situation whereby the nth row is this format. You see, so you may get a situation whereby the nth row is of this form 0, 0, 0, 0, then some number there, which I can just play k, where k is not equal to 0, like that, you see, but it's just some real number. So this is one of the things that may arise most of the time when you are given a system of n variables and you express it in echelon form. You may get some stuff here. We don't care what you get here. You might get some ladder thing whereby your pivots are dropping like that. But what we care about is the nth row, not just the bottom row. You see, so be careful. The reason why I had to state here like the number of variables that we're solving is because when we express a matrix in echelon form, it is the nth row that should be our main focus. Because sometimes mathematicians, they can trick you. They can give you a system of n variables, but in its augmented form, they give you something whereby there are n plus 1 rows. And then they give you a format at the bottom, which follows maybe the same pattern as what you are used to. Then they ask you about the nature of the system. Then you just check there and rush and say, this is it, then you get everything wrong. So you must always know that whenever you're talking about a system of n variables, the row that you must focus on must always be the nth row, like that, you see. So when you get something like this in mathematics, whereby you have an augmented matrix, which when reduced in echelon form gives something like this, whereby at the bottom, you have a sequence of zeros, and on the other side, the answer side, you have some real number, which is not 0, then always know that a system which gives you this has no solutions at all. So every time when you reduce a system in echelon form and this happens, just know that there are no solutions at all. You see. Then the other thing that can happen is that during your reduction process, you might get an identity vector on the other side, and then here you might get your vector B. So whenever you perform linear reduction, and then you get an identity matrix in this, or at times you cannot get just an identity matrix, or you can get an upper triangular matrix. You see, so it happens at time that when you are performing an echelon, reduction, you might get either the identity matrix or an upper triangular matrix. So when this happens, whereby on this side, or the coefficient side, you have what we call an upper triangular matrix, then you should always know that a case like this one tells you that you just have one unique solution. You see, so when this happens, you just have one unique solution. So these are the things that you must be familiar with when it comes to solutions of linear systems. Then the third thing that might is also a possibility that might happen again when you are performing an echelon reduction with a given linear system is that you can get an nth row again, which is just zeros everywhere. And also the other side, you have a zeros. So when this happens with a linear system, just know that it is one which has infinitely many solutions. You see, so when you reduce an n variable system and you get something whereby the bottom row is just filled with zeros throughout in the nth row, then you should know that you have infinitely many solutions in that case. So these are the things that you have to know in addition to what you already know concerning linear systems. So are there any questions that you have?
No, none for now.
Okay, cool. So now let's practice a problem which is related to this. So an example. So an example of a typical problem that can be given in exam is something like this. So they say, for which values of H is the system or does the system, so let's put down the system x1 plus 5, x2 minus 3x3 equal to minus 4, then minus x1 minus 4x2 plus x3 equal to 3. Then we have minus 2x1 minus 7x2 equal to h. So we are given a problem here. So they are asking us, like, for which values of h does the system given there have infinitely many solutions? You see. So what h or what possible values of h can you plug in there so that when you are to solve this system, you are going to get infinitely many solutions out of it? For which values of h? So how do we go about solving such problems? So if it was you, how were you going to approach this problem anyway?
I would put it in matrix form, and
so,
then Gauss reduction to try and get it to its simplest form first.
Yeah. So first thing, I will put it in augmented form or the matrix form, as you say. So this will become 1, 5, minus 3, negative 1, negative 4, 1, negative 2, then negative 7, then 0, then like that, then negative 4, 3, h, like that. So it means now what we're going to do is we're going to consider this matrix and we are going to perform some reduction to write it in echelon form. So how can we go about that? You see, how can we go about that? So the first thing that I can do is I can check row 1 and add it to row 2, and then the input I put it in row 2. So what does it imply? You see, so it means row 1 will remain unaffected. So we have 1, 5, negative 3, then negative 4. So here I'm taking this row, I'm adding it to this. So what will happen when I take this and add to that? Do you see that here when I add this will become 0? So I'll get a 0 there. Then when I add that, I'll get a 1, then I'll get a -2, then here I'll get a -1, then the bottom row will stay as it is. Then yeah, it's just like that. So do you see now that here also one thing that I wanted to learn from this problem is how you present your work. The examiner must know what operation are you doing. So you have to show like how I've shown there. And then also you have to show where in which row the result is going. So I'm adding row 1 and row 2, but where am I placing the aftermath? So it's going to row 2, like that. You see. Then the next thing, I'm continuing from there. So I take what now? So what I'm going to take now, I'm going to take 2 times row 1, and then I'll add it to row 3, and the result I want it to enter into row 3. So what does it imply now? So it means the first rows won't be affected, they will remain as they are. So I'm taking 2 times of this to that. So 2 times of that to that, I'll get a 0. Then 2 times of that is 10. To that, I'll get a 3. Then 2 times of this is -6. To that, I'll get my -6. Then 2 times of that, I get -8. So I'll get h minus 8, like that. You see. Now, what's next? Now, what's next? So now we can say the top are now fine. So now let's deal with the bottom. So to deal with the bottom, now what I'm going to do is I'm going to take row 3, and from it, I'm going to subtract 3 times row 2, and then I'm going to put my result in row 3. So what happens there? So the first will remain like that. I'll have 1, 5, -3. Then 0, 1, -2. So now I know that this is subtracting 3 times that. So 0 minus that is just 0. Then here I have 3 minus 3, I get 0. I have -6 minus that. You see, this when you multiply by 3 becomes that. So we'll get plus, which will give us 0 again. Then I have this minus 3 times that. So I'll get -8 plus 3, which is h minus 5. So we get that, you see. So it means our system in reduced form goes to that. But now, what are we looking for? We are looking for a value of h, which is such that when it's plugged in there, we get infinitely many solutions. Can we spot such a value?
It would be 5.
It would be 5. Because we know that to have infinite many solutions, we require this third row because our system has 3 variables. So we require the third row to be having zeros throughout. So here, fine, everything is 0, but we require this to be a 0. You see, so h minus 5 must be equal to 0. So therefore, h has to be 5. You see. So this is the type of problem also that you should expect in exam, where they ask you all this stuff. You see. So are we clear with that now?
Yes, yes.
Okay, cool. So now that's all that we wanted to look at when it comes to linear system. Now let's move on to a new section, which is the discussion on inverses. You see. So now let's talk about inverses. Like that. So what is it that is expected of you when it comes to this section? So what is expected of you when it comes to this section is to understand what is the definition of an inverse, and also to to know how to find the inverse of given matrix, especially the 2 by 2 matrix? Are you able to do those two?
Yes.
Okay. Because me, what I want is just to highlight some important properties of inverses that you should know, and one familiar results which you should know how to actually prove them mathematically. You see. So now let's list the properties of inverses that we are aware of. So we know that inverses, they have a lot of properties, but there are these ones which you should know that the inverse of the inverse is actually the matrix itself. Then there is this one which says that the inverse of the transpose is actually the transpose of the inverse. You see. Then 3. Also, we know this one which says that the inverse of AB is actually B minus or A minus, like that. Then 4, there is, yeah, so these are the properties actually that you have to know. And then 4 is a theorem, which is actually important also, which says that the inverse of a matrix is unique to that matrix. You see, so the last 2 results, they are actually, you are supposed to know how to prove. These 2 results, they are very important to know how to prove them. So there are questions whereby most of the time they ask you to show that this actually is true. You see, so even this theorem which says that the inverse of a matrix is unique to that matrix is a result which is quite important, and you have to know how to actually prove that result. You see, so how do we go about proving such a result? So we'll start about the proof of result 3. So the reason why I've decided to do this is because a linear algebra is a subject where you have to practice also how to write your mathematics, you see, using algebraic notation rather than just going through explaining stuff. You see, we want you to use that notation in a more convincing way that this is actually it, nothing more. So now how can I prove that the inverse of AB is actually that result? That is, I have there. So remember, what is an inverse, if I may ask? What is the inverse of a matrix A? You see, so recall, if B is the inverse of A, then what? Then we know that AB equal to BA must give us the identity matrix. Still recall that. You see, that the inverse is that matrix which, when it multiplies the other, we get the identity matrix as a result. So the question now is, they're asking us that if you take AB, is this its inverse? You see, so what you can simply do, you can now say, let C be the matrix AB, and let G be the matrix B minus 1, A minus 1. You see, so you can consider this. You can take now, you want to prove that this, what you have here is an inverse of this. So these 2 things must satisfy this property, that when you multiply them, you get the identity matrix. So let's see that is the case. So now let's multiply C and D. So what is CD? So CD is going to be AB times B minus 1, A minus 1. So we know that brackets can be put anywhere. So first I'll bracket here, what will happen? So we know that when I bracket there, I'll get B minus 1. Remember, B is the matrix and B is this inverse. So this will give us the identity matrix, as we know, which gives us that. But we know that the multiplication of any matrix with the identity does not change. So we'll remain with A minus 1, which gives us I. So CD is giving us I when we multiply. So what does it mean? it's telling us that this, what we have here, is actually the inverse of what we have on the other side. So therefore, you can now conclude and say, therefore, C and D are inverses of each other. So you have proved your result just there, because the only goal is to show that the inverse of AB is actually that, which is what we have shown there. You see. So are we clear with this?
Yes.
Okay, cool. So now the other results that you should also, you should know how to prove the uniqueness of inverses. You see. So how can we prove the uniqueness of inverses? So to prove the uniqueness of inverses, it is something which is very simple, but most people, they are not aware of how to actually do it. So we're going to learn how to actually prove uniqueness. So every time when you're asked to prove uniqueness in mathematics, you should always first understand what we mean by uniqueness. We know that uniqueness, it means there is only one of that kind. You see, so when we say a matrix such as A has a unique inverse, it means there should be only one such inverse. There cannot be two of them. So in order to prove that the inverse is unique, I'm going to first assume the contrary to that. You see, so I'll assume that both B and C are inverses of A. So now I'm assuming the contrary. I'm assuming that both B and C matrices are both inverses of that. Now what I'm going to do is I'm going to show that actually these two things are just one and the same thing. You see. So what I'm going to do now, I'm going to take one of these inverses and see how I can do some manipulation. So I know that I will take C or I'll take B. So do we agree that B is the same thing as BI?
Yes.
You see. So we know that B is the same thing as BI. Then now, do we agree that I can be written as a product of A and C?
Yes.
Because remember, AC is equal to the identity, because we said C is the inverse of this thing. So when C multiplies this, we must get I, like that. But remember, matrices, they satisfy what we call the associativity property. So it means this can be simplified by bracketing B and A first, while it's leaving C out. Are we cool with this?
Yes.
You see. So now what do we know about this thing inside the bracket? Do we say that it's also equal to I? So we get C, then this gives us C.
Yes.
Because remember, we say B is an inverse of that. So B and A must give us back the I, but I and the C, nothing changes, is C. So we started with a B, and we have shown that B and the C are the same. So we have actually shown that the inverse is unique for matrices. You see, so there is just one of that kind. There are not many of them. So whenever it exists, there is one of this kind. Because one thing that you have to know is that an inverse can either exist or not exist. When it's there, we say a matrix is non-singular. When it's not there, we say a matrix is singular. Like that. So are we cool with that?
Yes. Yes.
Okay, cool. So now that's it that you have to know about inverses, in addition to what you already know. Now let's talk about determinants. So determinants now. So yes, determinants as also at this point in time, you are expected to already know how to evaluate them, how to find the determinant of a given square matrix of any order, you see. So are you fine with that? Given a matrix, a 2 by 2 and 3 by 3, are you fine with finding their determinants?
Yes, I am.
Okay, cool. Because this is one thing that you should be familiar with, because now the only thing that I want to discuss is also the properties of determinant. Because the determinants, they have nice properties that you should always recall in your mind all the time. So I'm bringing it here so that we can just go through it again. So now, what are the properties that are associated with determinants when it comes to linear algebra? You see. So one of them is that the determinant of the transpose is actually equal to the determinant of the matrix itself. Then two, you should also know that the determinant of the inverse, which is a minus 1, is actually equal to 1 over the determinant of a. And three, what else? So also we have this very important result. You say that the determinant of the product is actually the product of the determinant. So I think these are very easy to recall and very familiar in linear algebra. But we have these ones also results that can be quite important in mathematics, you see. So it says that if A is a triangular matrix, then the determinant of A is just AII, you see, like this. So how do we interpret this statement? So this statement is trying to tell us a very important result, that every time, do you understand what is the meaning of this notation anyway?
Is it a sum?
No, it's not a sum, but a product.
Okay.
And do you see that here I've used two similar subscript notations? So what does it mean? It means I'm talking about the diagonal elements. You see. So from I whatever to N. So it means I'm talking about the diagonal elements. So this result is trying to tell us that if you are given a matrix which is upper triangular, the determinant can be simply found by finding the product of the diagonal elements. You see that? So it's quite a nice result, because you cannot waste time when you are given an upper triangular matrix or a triangular matrix in general. You just have to check only the product of the diagonal elements. Then 5, we have another also special result, which says that the determinant of Ka is actually K to N times the determinant of A, like that. Where N is the number of rows that matrix A has, you see. Right. So it's also another quite important result that you have to know when it comes to evaluation of determinants, like that. You see. Then there's this one which says that if A is a row of zeros, then the determinant of such a matrix A is equal to 0. So any matrix which has a row of zeros, its determinant is 0 as well. You see. Then 7 is actually a lemma of this theorem, but we're going to state it also as another result. If A is 2 similar rows, or even columns, then determinant of A is equal to 0 again. You see. So do you actually see that 7 is a consequence of 6? This actually implies this.
Yes, I do.
Because you can perform a row operation so that this matrix in 7 can have as a row of zeros, then it becomes 0. Because there is also this result, which is quite nice, which says that row operations do not change the determinant. So are you familiar with the other one? Okay, this one, which says that row interchanges affect the sign of the determinant. You see, so if you interchange rows of a matrix, you only change the sign, you do not change the value of the determinant of the original matrix, but you should always know what is n. N is the number of interchanges that you do. You see that? So if you perform one interchange, you only have a determinant which is negative. 2 interchanges, you get a determinant which is positive. 3 interchanges, you get another determinant which is negative, like that. So it's also another result that is quite cool to know again. Then the other one is 9, which says that addition of rows or multiples of rows does not affect the determinant. So that's another quite important result also when it comes to determinant, that when you add together one row to another or a multiple for another row to another, then it's quite, it does not affect the determinant. So i.e. if A is equal to ek minus 1 dot to E1 of B. So here I'm giving you a matrix which is obtained by row operations of another matrix in B. Then determinant of A is equal to minus 1 to n times determinant of B. So we can generalize all this in one line like that. So all these two have been generalized like that, you see, which simply means that if all these things are not any interchanges, if all these operations are no interchanges at all, then this is stripped off, then the determinant of A and determinant of B are the same. But if interchanges are involved, we count how many of them are there, then we place the value where there is n, then you will get the answer that you need, like that. So these are quite important results that you have to know in linear algebra when it comes to determinants, again, you see. So this is all in addition that I want you to know when it comes to this stuff. But what we are going to do now is we are going to then look at another last example, which can allow us to practice what we have learned already. So we are given a problem here which says show that if U transpose times U is equals to I, then the determinant of U is actually plus or minus 1. How can we show that this is actually true? You see. So to show this result that is given to us, one of the things I'm going to consider what is given. So I'm told that U is equal to I. So what I'm going to do, I'm going to find the determinants of both sides, like this. So here I do not know actually what the determinant is, but I know that whenever I have two matrices, I can break this to become that of UT that of U, and the determinant of the identity matrix is just 1. That's one thing that I know. And then again, I know that the determinant of the transpose is just the same as the determinant of U. So I'll have dtu squared is equals to 1. So I can now root both sides, root here and there. So therefore, I'll get that my determinant of U is equals to plus or minus 1. So that's it. So these are the kind of problems that you must expect most of the time for exam cases, whereby they are testing you that you understand properties of certain operation that they've taught you along the way. So there are many of them that we do not touch on. There are transposes, there are symmetries, anti-symmetries, all those stuff. They can ask you questions based on that to just see that now you know how to write your mathematics in a more understandable way. You see. So that's all that we have for our first session, covering the objectives that we've wanted to cover today. So
sorry, it broke up.
Oh, it had broken up. Sorry.
Yeah.
Okay. So I was just saying that here. So my question was, did you see me solving that problem? At what time did